every time a physicist says to you, quantum physics has demonstrated that a particle can be in two places at once, they are lying to you.
Biology, consciousness, causation, and quantum physics, what is the connection? My name is Curt Jaimungal, and this was part of my 3-day tour of Harvard, Tufts, and MIT, where I recorded 5 podcasts, including a frolicsome salon discussion hosted by MIT's Manolis Kellis, one of the world's top computational biologists. A few weeks ago, Manolis graciously offered to host both me and Harvard's theoretical physicist and philosopher Jacob Barandes for a salon on the nature of quantum theory. This event is unlike any podcast that you've seen or heard due to the extemporaneous dynamism of the over 70 people who showed up within just a few days' notice. The other podcasts from this tour feature Michael Levin and Anna Chaunica, as well as a separate discussion, an over 7 hours long one, with technical and concrete information regarding Jacob's approach to indivisible stochastic processes. Subscribe to get notified. For now, enjoy this jazz-like conversation regarding fundamental questions such as, do quantum fields actually exist? What's the problem with many worlds? Do parallel universes solve anything? And what makes observers like you special?
So Jacob, can you just give us a little introduction into what you do? Tell us like maybe 2-3 minutes about your journey. How did you get where you are? What are you passionate about? What are you the most excited about? And, what do you think we should really, if there's one thing to know, what should we know?
When I was a little kid, I was really interested in the philosophy of mind. I didn't know it was called the philosophy of mind, but later I would realize that's what this was called. I was confused about why we existed and the nature of consciousness and all these sorts of questions. I had a knack for math, and I went to college, and I thought, well, if you like math and you like deep questions, then you do physics. And so I studied physics, and I had a good time. And then I went to graduate school, and I worked in high-energy theoretical physics. I did my PhD in theoretical physics. I had some difficulty connecting with the research that was going on in high-energy theoretical physics. It didn't connect with me at some deep level. And, over, my PhD, halfway through toward the end, I began to reconnect with my earlier interest in philosophy, in particular philosophy of science. I got very interested in a whole bunch of different areas in philosophy of science, in an area that we would now call philosophy of physics, and in related areas that are closer to the sciences, like quantum foundations. So when I finished my PhD, I started doing research in the area, writing papers. My partner in crime is right here, David Kagan. We were close friends and collaborators. Yeah. And I began interacting more and more with the community of people who work in philosophy of science, and I realized this was my calling. So I stayed on.
What is philosophy of science?
Good question. What is philosophy of science? So broadly speaking, and this is philosophy of science, it's not exactly, well, I'll say what I do in a moment, but philosophy of science, broadly speaking, has several parts. One part is the study of what it is that scientists do, right? So it's the study of the sociology of science. The ornithology of science. Yes. Scientists as birds, and we observe their habits. And there's the old line, right, that this form of philosophy of science is as useful to scientists as ornithology is to birds.
It's actually a valid point, I have to say.
That is. However, I will say
it might be helpful to the observers of the birds.
It's true, but when bird populations are suffering, you do want to call an ornithologist. So and I'm not saying that scientists are doing.
Birds don't try to do ornithology.
That's very, very, very good. Yes. But the other, major side of philosophy of science is to go deep into our best, most successful scientific theories, understand how they work, and either try to glean an understanding, a new way of thinking about traditional questions in philosophy, in particular areas of philosophy like metaphysics, from what are best.
And what is metaphysics?
Okay, yeah, so good question. So
that was such a great question to ask.
These are all great questions.
Have you guys heard of the program called ELIZA?
Yeah.
It's at that level.
You've learned well from Eliza.
Tell me more about.
Tell me more about the thing you just said. Okay, good. Yes, right. For those of you who know, Eliza is this very old computer program. It was a computer therapist, and whenever you would tell it, it would just say, "Tell me more about," and it would just insert whatever you said.
and people spend countless hours.
Exactly.
And people spend countless hours on it, like pouring their heart out.
So metaphysics is a very broad area in philosophy. It's concerned with some of the most fundamental questions about the nature of existence, questions about universals, and it's questions about the nature of time and the nature of So one area. So there are areas of metaphysics that in philosophy of science we tend to spend a lot of time thinking about. So these are questions like, what is a law of nature, right? What are laws of nature? How do we identify laws of nature? And are laws of nature things that are out there in some sense, or are they things that we devise to make sense of the world around us? What is probability? When you say that a particular thing in the world is associated with a probability of 0.72, what information does that convey? Now, you pick up a book on statistics, and when I pick up a book on statistics, sometimes I'm interested in understanding, how they calculate things, but I'll often pick it up and look for where they say what a probability is supposed to be.
I feel like we should have some metabiology, because metaphysics is extraordinarily powerful about understanding the nature of the universe, but there's something about biology as well that's so fundamental as to why are we thinking, why, is there a soul? What's the neuronal basis of consciousness? Come here. See,
Wolfram has his metabiological framework, and so same with Gregory Chaitin.
Say it again?
Stephen Wolfram has metabiology, and Gregory Chaitin as well.
That's very, very interesting. Good.
Yeah. So, but I should say that metaphysics has the word physics in it, but it's not physics.
Yeah,
it's the things that metaphysicians and so metaphysicians, they're not called metaphysicists, they're called metaphysicians. Just to make very clear, they're not physicists.
That's so confusing because
very
physicians
confusing.
are a whole other thing.
It's very, very confusing. The name just goes back to the fact that there's a chapter in Aristotle. It just comes after, and meta just means after. It's the next chapter. So
if anybody should know, it should be the Greek guy.
Physics simply means natural. Physiki is just natural. So the natural sciences is actually physics.
Well, I mean,
to the Greeks, I'm sorry.
Physicists used to be called natural philosophers, right? I mean, that's what they were called. But so metaphysics is concerned with questions that are broader than any particular science, and that are relevant to and the questions that metaphysicians often. So here's a really intense metaphysician talk. Is there what is the precise way to characterize the difference between hypotheticals and counterfactuals? This is the kind of thing that, literally, these are the talks that you'll see.
They're very different things.
They are very different things, and we know they're different things, but, to spend a lot of time thinking carefully about it, that is the kind of thing that some metaphysicians do, right?
Can I hear what Manolis thinks is the difference?
Yeah.
So I'm going to come back to that in a second, because I have a few more things to ask, which might fall into metaphysics, and I hope we get to those questions. You don't have to answer them all right away, and I also want to get to Curt in a second. But one of the questions that I have is, does it matter that we exist? In other words, if you look at the whole biomass of the universe, the Earth is insignificant, and humans within it are, even more so. But if you look at the amount of consciousness or the amount of theorems or the amount of, heartbreaks in the universe, then we play a very big role, at least in my view. And what's really interesting is that at the heart of quantum physics lies an observer.
Some would say.
Some would say.
Some would say.
So basically, what I want to ask you is, does it matter to the universe that we are here?
Does it matter that we're here? So,
Jacob, is this reverse anthropics?
Reverse anthropics.
Ooh,
That's good.
Go tell us more. And introduce yourself. By the way, this has already started. Don't think that this is the first question. We're in it.
You can all ask a question. This is an intellectual exchange. This is a salon. People should just be asking questions.
I want everybody to feel that they should be answering as much as asking.
Pick up the thread, right? So this is a reference to the anthropic principle. The anthropic principle was coined by Brandon Carter, who is a theoretical physicist who works on deep questions in gravity. A colleague of Stephen Hawking. And the anthropic principle it comes in various gradations. One version of it is just, when you look around at the world and you see that it has certain features, Some of those features may be the way they are because they're laws of nature. Some of them may be the way they are just because they're random contingent facts, but some of them may be the way they are because of a selection effect. For example, we look around and we're like, oh, the ambient temperature around us is this nice temperature between freezing and boiling. Is that because of some deep reason? And the answer is it's anthropic. I mean, we wouldn't, as carbon water-based beings, be in an environment that had a temperature that was markedly different from that. So the fact that we see that is an effect of us being the humans observing it, and that's called an anthropic effect.
I want to build on that a little bit. I volunteer for my kids' schools, and one of the things that I volunteer to do is to go answer all of the questions that they have about the universe. So... Small task.
A small task, yes.
So for 3 weeks, they gathered questions. And, then I prepared for that talk more than I have to admit, any talk that I've given in the last 15 years at least. And one of the questions was, why is the sun so bright? And I used exactly the anthropic principle to basically say that if we lived in Jupiter or even in Neptune, the sun would be just as bright. In other words, there's a range of brightness that our eyesight has evolved towards. And at the tail end of that distribution lies the sun. And there's really no selection to be able to see the sun clearly. And I'm guessing that so many other things just feel completely natural because we basically evolved here. But there's another aspect which I thought you were going to get to, which is what...
Well, you didn't interrupt me. So well, but to be clear, I might have gotten there.
We only have an hour for, 3 hours worth of material at least.
It's okay.
What I want to ask you is, what I thought you were going to get to is not just that, yes, biology is well tuned to the physics that we kind of like and enjoy, but of course there's a weirdness about the fact that, for example, water, when it freezes, rises to the surface.
Yeah.
That is fundamental to why life exists at all. And I think that's a more fundamental principle than the fact that the temperature is well suited to our evolutionary adaptation. But what I thought you were going to get to is that as we observe the universe, we're observing perhaps a tiny fraction of maybe the dimensions that exist out there. And there's the laws of physics that we have come up with are a tiny subset of the things that are observable to our biology, if you wish. Am I completely off on this?
No, not at all. So one way to visualize just how epistemically limited we are as beings is...
Another Greek word.
Yeah, and there you go. Philosophers like epistemology.
So sorry, I have to say that episteme was one of the 4 virtues in the library of Celsus in, what is now Asia Minor, in the old Greek.
What were the other ones?
So the other was arete, which literally means virtues, to be virtues. The other one was Sophia, wisdom. So it's really nice to sort of have like episteme, which literally means science, but basically the study of things. Anyway.
Yeah, so one way to visualize this is to borrow from a geometric tool that was introduced by Hermann Minkowski. So Hermann Minkowski took the nascent theory of special relativity that Einstein was developing in the early part of the 20th century and provided this sort of geometric picture he called space-time. And so space-time, you visualize... like think of graph paper, right? Graph paper, the horizontal direction on the graph paper is all of space and the vertical direction is time. And you can visualize everything that ever happens as lying somewhere in this diagram. So each of you is a worm in the space-time diagram, a worm that begins somewhere down here and extends some length up here and then no more.
Lots of little worms come out.
Oh, maybe little worms come out. Exactly. Whereas, events that take place very quickly and then go away are more like points in this sort of space-time picture.
I think about it slightly differently as cones into the possible past and the possible future for every point.
So exactly. So the fastest anything can communicate a signal through space is at the speed of light. And so if you take any point and consider the light rays that can extend from that point or the light rays that reach that point, they form these things called light cones, right? The light cone gives you a way to visualize what can influence you in a causal way and what you can causally influence.
And also
what
when.
information can get to you.
And also when.
And also when. Yes, exactly.
Basically, whenever the cones
That's
intersect.
Right. That's right. Yeah. So think of it like this.
Can I interrupt? Nick Patterson.
Nick Patterson, one of my favorite
There's
people
a
in the world.
question, actually, what you mean by causal there. Because, as I expect you're going to come to, we have non-locality in
Yes.
mechanics, and what causes what is not so obvious.
The metaphysics of causation is dear to my heart and one thing I would like to talk about. So,
Well,
very
why don't you
apropos,
right
but-
now?
Yeah. Well, let's quickly finish this other thing
We're
first.
only
before we
on
do
the
next thing.
17th interruption.
I see how this works now. This all makes sense to me. All right.
So, Curt, I think I know our task. What we're going to do offline is we're going to go off and finish all these conversations. How about that?
Good. Excellent.
Okay, so it's okay to just keep changing topics.
So if you look at all of human history,
I have a question. Can we bring you back to the quantum physics?
we
yes,
are in
right.
quantum physics.
We took very fascinating first exit from the highway. For the uninformed audience.
We've hit a few more highways since then.
we've hit a few more highways.
Well,
yes,
I have a
good.
question about quantum physics.
Sure.
All right.
Okay.
So what is the... What
Nice
is
to
the-
see you, Curt.
Hi, nice to
Curt,
see you. It's
Curt,
been a
can I
while.
ask you a question first? So Jacob came here to talk about quantum physics. And we've been talking a lot about a bunch of different tangents, but I asked him a few very simple definitional things. And you are the host of a podcast called Theories of Everything. Or is it Theory of Everything? Theories. And I'd like you to just very briefly introduce yourself as to sort of how did you get to where you are? Why the heck did you start that podcast? And what have you learned also that shook your own worldview? Because one of the goals of your podcast is to disseminate knowledge to the rest of us. But another one, I hope, is for you to also, figure it out. And there's very few people who are so actively asking so many extraordinary folks about that one question that unified is it all. So tell us, what does Theories of Everything mean to you? And are there some surprising things that you did not know that were whoa, realizations that happened on your podcast?
Almost weekly. So as for how I got into this, firstly, any story I concoct will be a confabulation because, of course, after the fact, you can find the path
I
between
like the
points.
root of both fabulous and fable are the same.
Can we move on?
But since I was a kid, I've been interested in puzzles, abstract mathematical puzzles, and I was always interested in math and physics. One time I was thinking about the nature of the universe and how did anything come to be, and I was asking my brother who was studying math and physics at I believe the University of Toronto, or UBC at the time.
It is your brother.
So I was 8 years old and we were walking to Blockbuster, if you remember Blockbuster. And I asked him about how could anything come, how did something come from nothing? And then he explained to me what quantum fluctuations were. And then I remember going home and looking at the ceiling and then thinking, okay, then there is no God. And then I just became an atheist from that point forward.
Or if
Like
there
an
is, he rolls
Adamant's-
dice.
Sorry?
Or if there is, he rolls dice.
Well, okay, then there's no need for a God
Good answer.
in my 8-year-old mind. And then I remember telling some schoolmates about that. Then they're like, quantum fluctuations? And then I remember feeling so embarrassed because they were like, what are you talking about? And then I never said the word fluctuation until I was 18 after that. Then I was great in math and physics in school, so I was encouraged, and I went into that in university. And I left that because I was doing stand-up comedy and filmmaking. Yeah, so... Oh, and that's another story. When I was doing filmmaking, then the pandemic occurred, and I thought, okay, I was watching some podcasts online. There's this guy named Donald Hoffman, who has this theory of consciousness, at least supposedly a theory of consciousness that reproduces quantum mechanics, perhaps even gravity. I don't know if he's made that claim. But many people were interviewing him, and they're just in awe of Donald, and they're not asking any what I would consider to be rudimentary questions that are slightly pushing, not even antagonistic questions. And Donald keeps making reference to his papers. He's like, I can prove this in my research. And then I was thinking, okay, so are there any people here who are reading his research and then speaking to him? And I couldn't find any. So I thought, let me reach out to him and read his research and then questioned him about that, and it was quite a technical interview. So I treated the podcast like office hours, and I was even going to call it office hours instead of Theories of Everything initially. And that's how I still treat it. Like even when I was speaking with Jacob yesterday, we spoke for 7 hours as if, and you even have classes where, well, potential classes where they could be 7 hours long. They don't last that long, but we spoke for 7 hours.
I just go until the students give up. It's an endurance contest.
The class can last that long, but the students won't.
And I'm extremely interested in the nature of reality. What is this? You mentioned metaphysics. You mentioned epistemological limitations. And so one of the issues I have with principles of anthropic principles is we're speaking about life as we know it. Now, I know you have some claims about life as we don't know it must be similar to life as we know it. I find that dubious.
It must have similar properties. I hope not DNA. Like DNA would be such a boring thing if we find it elsewhere.
Well, anyhow, so it's not clear to me that this is the typical state. So red giants last for trillions of years?
Red dwarfs.
Red dwarfs last for trillions of years. We don't know if there's some life form in the sun, and the most typical life form would be a conscious agent in the sun, or if we invent AI and AI takes over, and AI has many, many trillions, billions, trillions, other direction, billions or trillions of times more conscious experiences than us, and thus the most typical conscious experience is us being an AI or gray goo. I don't know if this is the most typical. I don't buy these anthropic arguments. Furthermore, you can't look at quantum fields and derive biology, let alone it's difficult to derive chemistry. It's somewhat easy to derive chemistry when you know where you're headed, but it's not clear to me if you vary the laws that then you can't have life as we don't know it. Like we can, okay, so anyhow. That's what the podcast
so
is
in
about.
the
Is
end,
investigating
you actually care
these
about
issues.
life in your podcast. It's not just about physics.
Well, you asked about what
unification.
matters, and then you gave this my standard atheist 8-year-old response, which would be, oh well, we don't matter because we're a speck of dust among many stars, among many planets, and then you look at the world spatially and you say, well, because we're insignificant spatially, then we don't matter. Well, why are we privileging what happens spatially? Are we to say that what happened at Auschwitz, oh, it doesn't matter because you were just a tiny moment in history? I think what happened there matters. And I think when we start saying that we don't matter, then you have to question your definition of matters. Or question, why do you think what matters matter? Matters.
All right. Feel free to jump in, anyone. Burning questions.
More stand-up comedy.
So when I was 12 years old, I asked my mom, hey, Mom, did God sit around completely bored out of his mind for the first 13 billion years until life started evolving on the planet, and then for another 3.8 billion years until we finally evolved so that we can honor him?
Nice.
And my mom answered in the most mind-blowing way. She basically said, Manolis. And I was 12. Manolis, do you think that the creator of space and time experiences space and time the way we do? And that blew my mind. And one of the problems that I have with praying and miracles is that if I pray for something to happen, for my friend to show up, that prayer better go back in time, affect my friend, who will then decide to start taking a trip and eventually show up and see me. And if instead, whatever supreme being experiences time and space differently, they can answer my prayer by affecting things in a non-causal way.
That's something I think about as well. I don't know if there's a creator, but something I think about is we often, even if you're an atheist, at least sometimes you think, oh, I wish so-and-so doesn't happen, or maybe you get a diagnosis and you wish it's not going to be serious. And then you have no idea how many of these wishes have come true already, that you've prayed for, or that you've prayed for in some alternate timeline and it's come true.
Yeah, somebody heard your prayer and has been working on it for your prayer to come true. You can't just wish for something now. You have to, wish for something to have started happening. There's an episode of The Simpsons where...
always an episode.
Gotham, where Bart basically finds this hand and he can wish for things. And, every time he wishes for something horrendous happens for that thing to come true. And I think the physics implication of that is that you have to go back in time, to create an alternate universe where that wish is true. And by your words, it just messes up the whole universe. But the way I'm imagining it is, in a not messing up the whole universe, space-time continuum kind of thing, where you can sort of still wish for something and then somehow, so I'd love to hear your thoughts on that. So basically, we've talked about these cones of intersections, and how would you envision miracles? Or is there a possibility for some other type of form? It doesn't need to be the creator of the universe, but it could be some other occupant of the universe that doesn't actually obey causality and constraints. And maybe, quantum could be one of those things where you basically have these long-range influences.
I'm going to pull the most annoying philosopher trick ever, and I'm going to return the question by asking, what do you mean by miracle?
I think it's pretty clear from the context.
He's a philosopher too.
What people thought were miracles 100 years ago happen now all the time.
Right,
500 years ago, right? I have a technical question.
Sure.
Is there any counter-argument to quantum gravity that you think is... do you believe string theory is a good theory, or do you think...
Well, string theory is not a belief system.
Tell us about quantum gravity and string theory.
Quantum gravity and string theory, okay.
But also, to make the question clear, when you say a counter-argument to quantum gravity, you mean a counter-argument to the existing theories of quantum gravity, such as string theory, or a counter-argument to the idea that gravity must be quantum? Because those are different.
To the theory that gravity must be quantum.
Gravity must be quantum. Well, this devolves down to the question of what you mean by quantum, and that's sort of what I've been thinking about for quite some time. Yeah. So the standard way we think about quantum theory is there's a very important role played by the observer. There's an intricate mathematical apparatus, and this mathematical apparatus it engages in a form of quietism about what's really out there. But what it does is it delivers us a precise instrumentalist recipe for telling us what will happen when you do certain things. When observers do what's called a measurement on a quantum system, the theory furnishes a probability for getting a particular kind of outcome. Right? That's what it does. But it doesn't tell us what's going on in between. So when you read a book about modern physics, you read a book about quantum mechanics, and the book says, well, the reason why this particular thing happens is because this electron's going like this, and a photon comes off of it and does that. As far as the standard way that we teach and formulate quantum mechanics today, the form of quantum mechanics you find in all the standard textbooks, all of that is just for color. All of that is just fables. The theory only says that when you have an observer, and the observer does this particular thing called measurement, then there will be these results with these probabilities, and that's it. It doesn't furnish anything else in terms of a physical picture. Now, that's the standard way that we teach, it's in the books, but of course people have been dissatisfied with this picture for a very long time. And one of the things that Einstein was dissatisfied with about quantum theory, it wasn't the probabilistic aspect of quantum theory. It wasn't that God played dice with the universe. He could live with that. After all, one of Einstein's great breakthroughs was Brownian motion, right? Which was instrumental in us understanding the nature of atoms. It was, one of the papers that was part of his great year, his Annus Mirabilis in 1905. So probability wasn't the issue. For him, it was that there wasn't a metaphysical picture of what was out there happening between the measurements. And so one concern you might have is that maybe quantum theory is such a weird mathematical theory that any time you try to propose some kind of physical reality, a so-called ontology, Greek word again, right, for what's going on behind the scenes, it's going to be the kind of ontology that is inconsistent with the mathematical apparatus. So the worry was that the mathematical apparatus of quantum theory was over-determined. It was too constraining, and no picture you possibly could write down could be a picture that was compatible with quantum theory working. Right? This was the worry I think a lot of people may have had. And so the attitude was, we just shouldn't talk about what's going on. And this became known as the Copenhagen interpretation. The Copenhagen interpretation just says, our brains cannot understand what's going on between measurements. All we can talk about are measurements. Measurements are done by big, classical objects like us that obey classical rules of physics. And what's going on in between the measurements, we can't understand that. We have a mathematical apparatus for it, but we can't actually visualize it or write a picture down. And that's, we're trying to fill that picture. We're trying to fill that picture in.
Let me dissect that one word, which I think might mean two things. The word goes on between measurements. There's two types of betweens. There's between in quantum time, if you wish. There's between, of course, observations, but there's also between in quantum space. And the real numbers are a beautiful thing, but they might be completely fictitious because the physics of the universe don't obey real numbers. And then there's another, I'm not fond at all of the whole simulation hypothesis. Terrible hypothesis. But
I've known too many computer programmers, so I'm skeptical.
however, one interpretation of quantum physics is that there's just too much to compute. And therefore, you don't compute something, you have a lazy computer. That physics is basically running lazy computation. And
this is why there are all these uncertainty principles.
Computing everything.
Yeah, right.
And it's only when you sort of try to look up a variable that actually computes it. Can you debunk that idea? Sorry?
Can I introduction?
Of course.
I had a good point here.
What's your name?
Shresh.
Introduce yourself.
I'm a freshman at Northeastern. I recently started working at the Media Lab as a researcher, and I started getting into all of this. But what I was working on a few days ago was actually inspired by your post on Twitter about Lagrangian submanifolds. It was really impressive.
That is very cool. This moment must feel very good to you, right? Inspiring the young generation is so great.
What the student is referring to is my post on Lagrangian submanifolds, which went viral on Twitter, LinkedIn, and Substack. Feel free to follow me on Twitter at @ToeWithCurt. On LinkedIn, you can add me by searching for Curt Jaimungal. And for Substack, you can visit curtjaimungal.org. Links are in the description.
That is very cool. This moment must feel very good to you, right? Inspiring the young generation is so great.
So I have like a GitHub repo where I had like a bunch of Python notebooks which I was working on, and I used like a program synthetic approach to try to prove some natural laws using Lagrangian submanifolds, and it was actually working. Like I was proving conservation of energy, and both from the classical mechanics and the quantum mechanics side of things. And honestly, it was interesting because I don't think the in-between factor is in fact being computed, like you were saying. Because if you're able to compute functions from natural laws, the functions from natural laws, from such a probabilistic approach, it's so weird that you can end up with both approaches on the macro scale and the quantum scale. So I think it's completely unsolved, the gaps between everything that we
in space, in time, or in computation?
In terms of computation.
Cool.
Yeah.
I'm Aviram. I'm
Introduce yourself.
Experimentalist. Can you explain what you mean by the in-between is not computed? All quantum mechanics does the in-between, right? It tells you, okay, in between you have a wave, it propagates according to Schrödinger's equation, and then if it interacts with a degrees of freedom system, whatever classical system.
It's nice to meet you. That's a very good question. Thank you.
There's some seats in the back. Do you mind coming and sitting on the white chair over there? The white cube?
Yes, I'll repeat the question. Yeah, so the question was...
Is this good or bad?
We have the tomatoes.
Notice there's a few more chairs.
Let me repeat the question. The question was...
Why didn't he ask?
Yeah. Right. So the question was, what the hell could I mean by saying that quantum theory doesn't say what's going on between the measurements? I mean, there's the Schrödinger equation, and there's wave functions, and there's all this apparatus, right? So what Heisenberg meant when he talked about the Copenhagen interpretation. So he wrote about the Copenhagen, he introduced the term the Copenhagen interpretation. It's a chapter in his book, Physics and Philosophy, in 1958. And the way he described it was he said, okay, classical objects, those have physical reality. We understand what they are. They're phrased in terms of objects that live in three-dimensional space. But we don't have the mental architecture to understand the reality, what's going on with quantum mechanical particles, tiny particles. So we use this mathematical formalism, but the formalism is not real. It's not physical. The wave function is just a mental construct, just a piece of mathematics. There isn't really a wave function anywhere. And so, but let me turn the question back to you. So, classic move. Are you suggesting that you believe that the wave function is a physical entity in the way that, for example, a chair is a physical entity?
I can bounce the question back to you.
Okay.
Is a gravitational field, for example, or whatever, any field, is that a real thing or not, right? You were taught in, ninth grade
Yes.
that there is a field And what it tells you is that were you to put a particle in that electric field, it would sense a force which is measurable. Right?
Yes, yes.
It's a field, a real thing.
I'm going to take a stand, and I'm going to say that right now I think that fields are metaphysically real. Fields are localized intensities that are distributed physically, metaphysically. They are real in the same kind of way that I think chairs are real or that you are real.
Now it's easy. Now,
Yes.
Now it's easy to take that stand. I agree with you.
Yeah.
And now we're not in ninth grade. We're already.
Yes.
And we know that.
But there's a reason for it. But there's a reason for it. The reason I think that fields are physically real in the way that chairs are is because fields are intensities in physical space. And you can, they propagate energy and signals around through physical space. And so I have good reason to think that they are physical things. Now, why don't I think that wave functions, that Schrodinger wave functions are physical things? Where do Schrodinger wave functions live?
In the complex world. The math.
Not just the complex world. No. They live in
our minds.
They live maybe in our minds, but if they were purportedly to live in some kind of reality outside of our minds, where would that be?
What about potential?
What about potential? I've got lots. How about you?
I'm too old for potential.
Yes.
No, I'm talking about Aronoff Bohm.
Oh, right. This question about gauge potentials. Do gauge potentials have reality?
Can you guys let us in? Phrase a whole sentence, please.
So the idea of the existence.
Please go ahead and explain gauge potentials to the yes.
The existence of a field, right? There will be like the real thing, the thing that you could measure because you have a force, and they will derive from some mathematical abstract object that we call potential that will be able to change based on the way you define them. So they're less real, but then you have physical effect like Aronoff Bohm, for which they are there, they have physical effect, but then the field is zero. And the question of which one is real, potential, field, in fact, we don't know. In fact, it doesn't make sense. It's not a very relevant question.
Now that the question is complete, can you now give us a little bit of an introduction for the rest of us?
Okay, let me see how to do this. I see Karen making it. Okay, I got this. Okay, so there are these things called electric fields. We know about electric fields, right? And we know magnetic fields. You've all been inside of an MRI, not everybody's been an MRI, but you know about MRI machines. You go to an MRI machine, they turn on a very strong magnetic field. Okay, right, good. I'm not going to talk about why they turn on a strong magnetic field because I don't have time to do that. We've compasses, right? Earth-based magnetic. So we have this electric field, this magnetic field, and these fields we model as little arrows everywhere in space, and they tell charged particles where to go. We have this usual picture, and we have a bunch of equations, laws that describe how these fields change with time. The laws are called the Maxwell equations. They go back to James Clerk Maxwell, okay, in the 19th century. Now, there's a bunch of these equations. The Maxwell equations are complicated. There's a whole collection of them. And it turns out there's a way to write them in a simpler way by introducing these mathematical things called gauge potentials. These things called gauge potentials are a little weird, but they're simpler. They have fewer moving parts. And you can boil down the Maxwell equations into a smaller set of equations for these potentials. And you might go, well, this is just great. Let's just take these potentials to be the fundamental things. I mean, they're kind of like fields. You can associate them with places in space. What's the problem? The problem is that they are not uniquely defined. There are infinitely many different, distinct configurations of the gauge potential that all correspond to the exact same electric and magnetic field. So you're like, well, I mean, does nature secretly have just one of them? But if it does, there's massive empirical underdetermination. We could never know what the true gauge potential is. And so what most physicists would say is the gauge potentials are not physical. The electric field is physical, the magnetic field is physical, and the gauge potentials are just useful pieces of mathematics, not altogether distinct from maybe how we might think of wave functions, just a mathematical tool to simplify the mathematical procedure. And that's what we might have thought. And then these really annoying people, so David Bohm and Yakir Aronov, decided to make our lives difficult and show that in some circumstances, when you have charged quantum mechanical particles moving through certain kinds of an apparatus, where the electric and magnetic fields apparently are switched off, but the gauge potentials are switched on, there can seemingly be empirically observable effects on the landing sites of the particles at the end of these experiments. And this raises the question, well, but if the fields are off where the particles are going, And the only thing that's on are these gauge potentials, but I didn't think gauge potentials had any physical meaning. How can they be producing an empirical effect on the behavior of the particles? I think that was pretty good time. Yeah. Yes, Shaoli.
Check, you said something which I think is, so there's some logical problem, right? 'Cause you said the reason you don't believe the gauge potential exists is because it's not unique. There are infinitely many of them. By that argument, the human does not exist. If you ask it, what is a human? There are so many of us, potentially there are infinitely many of us. Like, what is a human?
A featherless biped.
To pick up some more argument than just being not unique, right? Because you could massively define it as an equivalent class. You can always have a way to unique.
But there's no equivalence class for you, Shaoli. There is only a unique Shaoli.
Now you're being very classical.
Let me reframe it. Let me rephrase it.
There has to be uniqueness. Was that heuristic to use?
Let me pause for just 1 second and answer your question. I think what Jacob is basically saying is that if there's so many different ways to explain the reality by sort of having equations that are so powerful that they can explain this, but they're completely undetermined. For example, if I take I mean, that's one of my issues with string theory, for example, or one of the criticisms of string theory, that there are so many different possible ways of sort of creating today's world that it doesn't narrow it down, and therefore the predictive value for things that are not observable is very small because you have way too many parameters for the problem at hand.
Didn't I just give up on string theory?
No. Well, what do we? Does that?
That's just a matter of.
So undetermined rather than there are so many. Is that what you meant? Did you mean undetermined?
It's radically undetermined. So Shaoli, for example, I can do experiments on you and pin down which human you are, and eventually.
I'm not sure about that.
You're not underdetermined. In other words, are like.
Couldn't you though say that the gauge potentials encode aspects of reality insofar as, those aspects don't change when you change the gauge? You know what I mean? Like it's a redundant, it's not that they don't exist, it's a redundant description.
Yeah, so one way to think of a gauge potentials is like, suppose you want to describe Earth's surface, okay? And perhaps you believe like I do, that Earth's surface physically is there, but you want to describe it in some quantitative way. So you decide I'm going to work with latitude and longitude. You say I'm going to describe where things are with latitude and longitude. And then, you start building theories out of latitude and longitude, and you begin to believe, I think latitude and longitude are real things. They're physically there. Those lines, they really mean something. And then someone comes along and says, well, actually, I think that where I live should be the origin of your coordinate system. So I'm going to use this other slightly different coordinate system. And you go, you can't do that because we all know that the prime meridian is definitely a thing, right?
The Big Ben.
Right. And so, but when you realize, wait a second, there are infinitely many coordinate systems you can use to describe the Earth, and not just things that are akin to latitude and longitude, but you've got the Mercator projection, you've got all these different coordinate systems you can write down. You begin to wonder, because there's this there's no true coordinate system for the Earth. The coordinate system is really just mathematical descriptive tool set. And what's fundamental is the Earth's surface, right? And so the attitude here is that the electromagnetic fields are like Earth's surface in this analogy. They're the physical thing. And the gauge potentials are like different, coordinate systems we can use for these things.
Yeah. The gauge potentials are equivalent to the wave function in that kind of...
So John Bell, his name comes up a lot in quantum foundations. John Bell was a theoretical particle physicist who also did groundbreaking work in the foundations of quantum mechanics from the 1960s all the way through the end of the 20th century. He introduced a lovely word for distinguishing between things that we think, at least we have good reason maybe to think are physically real, and things maybe like wave functions or maybe like gauge potentials that we have reason not to think are real. So he was distinguishing between, so there's a term of art in quantum mechanics called an observable. An observable are those features of a physical system that observers go and measure: the position of a particle, the momentum of a particle, the energy, whatever. Those are called the observables. He wanted a word that was kind of like observable, but words for things that described how things could really be, ontologically speaking, like what they really were, right? What was physically there. And so he called these things Beables, not observables, but Beables. And you meet someone who's learned quantum foundations only from books because they come to you and they say, tell me about Beables. What are Beables? Beables.
Does anyone not call them that at some point? You go through an evolutionary process.
It's like going through the cocoon stage, right? It's the Beables stage, and then you're like, no, wait, I've seen the light, they're Beables. So what John Bell would say is that there are some things that are Beables, and he was very explicit about this. He very explicitly put gauge potentials into the class of non-Beables, as things that are mathematical appurtenances, artifacts of our description. And there are many other examples. There are many other examples. So here's an interesting story, okay?
But right after this, get ready for the next question. Raise your hands. Who's ready for the next question?
Let me go to the next question. I'll punt in the story.
Okay, go for it.
Yeah, go for the story.
Do the story? We'll do the story. Okay. So one of the most important pivotal moments in the development of quantum mechanics was the early 1920s. 1920s was a period when physicists decided they were not going to be able to come up with good laws that were going to be able to be empirically adequate based on the pictures they were describing. So you may know, if you took high school chemistry, you learned about the Rutherford atom, where the electrons are going in circles around the nucleus of the atom, right, in these sort of orbit. The people still draw these pictures. Well, up until the early 1920s, physicists were trying to make that work. They were trying to come up with a set of equations and laws that would build on that physical picture and be empirically adequate, meaning they would agree, they'd make the predictions that would agree with the things they're seeing in experiments, and they couldn't find the right set of laws. They were using all the different kinds of laws that they were familiar with, that they'd inherited from centuries of work in physics. And then in the early 1920s, people like Wolfgang Pauli and Niels Bohr began to doubt that this was possible. And Bohr had a pivotal set of conversations with Werner Heisenberg, who was very young at the time. He was early 20s. Bohr had already won the Nobel Prize, in which Bohr divulged his big secret. He didn't believe that there were orbits anymore, electrons going around it. And this, Heisenberg, processed this, was thinking about it, and then there's that in spring of 1925, Heisenberg was a PhD student at Munich, but he was visiting Göttingen, which was a center of theoretical physics and mathematics. He was working with Max Born and Pascual Jordan, and he was looking at all these formulas, and everything that Bohr told him was just sort of marinating in his brain, and he was suffering from a massive case of hay fever, the worst and most important case of hay fever in history, okay? Right? So think about it like this, right? You think that you've got hay fever or something like that, it's a terrible quality, you wish you didn't have it. Well, the whole history of science may be different if it hadn't been this case of hay fever, because Heisenberg was miserable. People said his face was so swollen up it looked like he got into a fight. And so he goes off to this island called Heligoland, where the tree pollen levels are very low. And he went with two goals. One was to memorize a huge amount of Goethe, and the other was to solve quantum theory. He accomplished one of these goals, one of them, okay? But here's the thing. He created a paradigm shift. In Kuhnian language, he created a paradigm shift in science. He said, I am going to banish the physical pictures. We should not be formulating physical theories in terms of pictures. We should formulate it only in terms of quantities that are in principle experimentally measurable. He says this in the opening lines of this. It is a philosophy of science, like 101, great paradigm shift statement. He says we're going to banish them and we're going to build a theory just out of mathematics. And this theory he builds eventually becomes what we call matrix mechanics. And it's a theory without pictures. It's a theory that's just raw mathematics. And this was the beginning of the end for the world pictures. Everyone was amazed. Einstein said Heisenberg had laid a great quantum egg, is how he described it, right? The idea that if you banish the pictures, suddenly you get equations and laws that seem to work and give the right predictions. And this was incredible, right? But then Schrödinger comes along right afterward and brings the pictures back. He brings pictures back, and he does it by introducing the wave function. And how does he get the wave function? It doesn't just come out of nowhere. It doesn't just come out of mathematics. It comes out of classical physics. It comes out of classical physics. So there's a way to take classical physics. You don't know force equals mass times acceleration, or force equals mass acceleration. Well, it turns out you can take force equals mass times acceleration. You can write it in mathematically very complicated ways. And there is a very abstract way to write classical mechanics. It's called the Hamilton-Jacobi formulation. And we almost never teach it to students anymore. Almost no students who come up in physics have ever heard of it anymore. But Schrödinger learned about it. And the Hamilton-Jacobi formulation, you reformulate classical physics in a distinctly wave-like way, with a distinctly wave-like quantity called the Hamilton's principal function, or the Hamilton-Jacobi function, which obeys this gnarly partial differential equation. And Schrödinger looked at this wave-like thing in classical physics. Now, to be clear, this wave-like thing doesn't appear to have any physical reality to it. It's just an alternative way to describe what all the Newtonian particles are doing. But he took this wave-like thing and the differential equation that it satisfied. He looked at it and he realized, oh my gosh, that looks like the iconal approximation to a wave equation. And I'm going to call the wave function that it's the, I'm going to call that the Schrodinger, the wave function. You didn't call it the Schrodinger equation, that was himself. That would have been very, yeah. But he uses this Greek letter psi for it, right? Maybe because that's the symbol of Poseidon and its waves. I mean, I've always wondered what that was, but he introduced this, but the wave function was an outgrowth. The wave function was an outgrowth of a clear mathematical appurtenance of classical physics. No one would have imbued the Hamilton's principal function, this weird wave-like abstract quantity that satisfies this bizarre partial differential equation. No one would have imbued that with any ontological meaning. And the wave function was a direct descendant from that structure. Now, physicists loved wave mechanics. Actually, he called it undulatory mechanics originally, which is just such a much better name.
So much
Undulatory
beautiful,
mechanics is so much more interesting. Anyway, called it undulatory. And physicists loved it because now it was back to differential equations, and they had this picture of this wave function. And Schrodinger, for at least 2 years, he took his wave function seriously as a physical object. He said, these wave functions, they don't live in physical space. They don't live in 3D space, the space we live in. They live in possibility space. And there are statisticians around, of course, parameter spaces. Wave functions live in parameter spaces, not physical space. And so Schrodinger found himself arguing, maybe a high-dimensional parameter space where wave functions live, maybe that is the seat of physical reality. And maybe in that reality, all the possible things that could really be happening to a system are all playing out in an embryonic version of the many worlds interpretation. He held this view for a couple of years. Now, many of you have heard of Einstein saying this famous quotation, "I don't believe God plays dice with the universe." That was in a letter to Max Born on December 4th, 1926. He says, quantum theory is very imposing, but I don't think it's the real thing yet. I, for one, don't believe that God plays dice. People don't know the next sentence in that letter. The next sentence in that letter. And they don't know the next sentence in the letter because it was mistranslated. In the canonical translation of the Einstein-Born letters by Irene Born, the next sentence was mistranslated. And I know this because I thought the English was kind of weird, and I went back and looked at the German, and the German was clearly different. And I put the German through Google Translate, and it was clearly a different translation. Here's the difference. In the English translation I had read, Irene Born's translation, the next sentence is Einstein saying, waves in three-dimensional space, as if by rubber bands, and he actually puts a little ellipsis, ... like he doesn't, and you're like, gosh, Einstein didn't like waves in 3D? That's a weird thing to say. I mean, Einstein certainly seemed to like light a lot. Light is a wave in 3D. But in the original letter, it's not waves in 3D space. It's waves in 3n dimensional space. She dropped the n, and that's crucial because when you have n particles, the parameter space is 3n dimensional. And what Einstein didn't like was that Schrodinger was asserting that the seat of reality was an abstract parameter space, and that Schrodinger was asserting that a physical mechanical wave in this abstract parameter space was the actual ontology of nature.
Can you explain to us what's the n? What is the number of particles? What's n?
So when you have one particle, quantum mechanics associates with that particle this thing called the wave function. And the wave function in the simplest form is a statement that at every point in space, if you were to measure where the particle is, the probability with which you'll find it at one point in space is given by a particular mathematical procedure done to the wave function. So you can think of the wave function as an assignment of kind of a number to every point in space. It's a bit like a field, if you want to think of it that way. And if I measure where the particle is, I'll get one of the answers, and what the field is telling me is where I'll find the particle. And this picture is how quantum theory is usually presented to incoming students, because incoming students will usually learn about quantum mechanics, the quantum mechanics of a single particle. It's like the first, 2/3 of the book is quantum mechanics of one particle. And they get really used to thinking, the quantum wave function is like a field in 3D space. Right. But here's the problem. The moment you've got two particles require 6 parameters now, you see, because you have to specify, if you do a measurement, you ask, where am I going to find the system, right? Where am I going to find the two particles? There's the x coordinate, y coordinate, z coordinate of the first particle, and then there's also the x coordinate, the y coordinate, the z coordinate of the second particle. And those 6 variables define a 6-dimensional space. 3 times 2 particles. N is now 2, 3 times 2 particles. And that's where the wave function lives. The wave function is a function who lives in this 6-dimensional configuration space. And for n particles, it's 3n-dimensional space. So Schrodinger took it seriously. He's like, I think maybe this is what the state of reality is. And then in 1928, in his 4th lecture on wave mechanics, he recanted that view. He said, Max Born has come along and said that the wave function is not a mechanical object. It really is related to measurement probabilities. And I just no longer hold this view anymore. But I think by then it was too late. And many physicists went on to think that wave functions were physical, just as physical as anything else.
Can we talk about the superposition now? Because we were talking about action at a distance earlier, and this whole concept of you have now these multiple particles, they can be in some kind of superposition. Explain to us a little bit about this whole action at a distance.
Yes. So the thing about quantum mechanics is that wave functions are actually reflections. So what Heisenberg was doing and Schrodinger was doing were actually just aspects of a deeper mathematical structure, the structure of Hilbert spaces. And this formulation of quantum theory in Hilbert spaces was done by Paul Dirac in 1930 and John von Neumann in his book in 1932. And in this picture, the state of a quantum system, if you want, you can think of it as it's basically the wave function. The state of a quantum system is the kind of thing that if one is possible and another is possible, then you can superpose them and that's also possible. So if there's a wave function that assigns certain probabilities to the particle and a different wave function that would assign different possibilities to the particle, you can superpose the two wave functions together. That's called a superposition.
It's very weird, right? That's very different than classical physics.
Yeah, it's different from classical physics. For example, if one of the wave functions assigns a very, very high probability to a measurement showing the particle to be here, and the other wave function assigns a very, very, very high probability of the particle being here, and you superpose the two wave functions, what have you done? Are you saying the particle is in both places? Well, the Dirac-von Neumann axioms, the standard textbook axioms, don't say that because they don't paint the picture at all. All they say is that if you have a superposed wave function, then if you measure where the particle is, there's some probability to find it here and some probability to find it here, and anything else you want to say about it, like the particle's really in the two places, that is, strictly speaking, outside the axiomatic ambit of the axioms. That's just for color. So every time a physicist says to you, I'm going to tell you, this is a secret, every time a physicist says to you, quantum physics has demonstrated that a particle can be in two places at once, they are lying to you. Now, I don't mean they're lying to you in the sense that it's definitely wrong. Maybe it's right. It could be right. But it's not right based on any interpretation of quantum theory we have, except possibly for the many worlds interpretation. None of the other interpretations, including Copenhagen interpretation, including
Can you now, in simple English terms, tell us what are those 3 or 4 interpretations?
3 or 4?
Yeah.
Oh, there's quite a few.
Well, tell us 3 or 4 of them.
And Jacob has his own, by the way.
Yes, we all get one.
Tell us the 3 dominant, and then the 4th will be yours.
So the instrumentalist textbook Dirac-von Neumann formulation just says nothing, except that you do measurements and we predict what we're going to get. That's it. There's very little interpretive work. The Copenhagen interpretation we already talked about, that's the idea that there are classical things, and the classical things follow classical laws, and quantum things we just used in mathematics to describe them, and between experiments we can't really say physically what's going on. That's the Copenhagen interpretation. In the 1920s, Louis de Broglie introduced the first pilot wave interpretation of quantum theory. And the pilot wave interpretation says that there are wave functions, but there are also particles, actual particles, classical-like particles that really are in certain places. And what the wave function is doing is guiding the particles around, piloting them. That's why it's called a pilot wave interpretation. The reason why you're more likely to find the particle in certain places where the wave function is stronger is because where the wave function is stronger is where the wave function guides the particle to.
My interpretation was that the particles manifest where the wave function collapses.
Not according to the pilot wave interpretation.
So they're actually physically manifested.
The particles are physical corpuscles, physical particles, yeah. And this was a very rudimentary picture that de Broglie put together, and it was torn to shreds by his colleagues at the time. 25 years later, David Bohm, the same David Bohm from the Arnav-Bohm effect, he was at Princeton. He wrote a book called Quantum Theory, 1951. He tried to explain the measurement process as best he could with, the standard approach to quantum mechanics. He presented his book to Einstein. Einstein was very dissatisfied, says, try harder. Bohm, the next year, publishes papers where he introduces independently the pilot wave interpretation, much more sophisticated, much more complicated, and along the way, invents a huge amount of important physics. Okay, and importantly, he introduces the concept of decoherence, which is one of the central ideas in practical realizations of. I mean, people talk about decoherence timescales all the time. This comes from the work of David Bohm, trying to make his pilot wave interpretation work. And this notion of decoherence, which I can talk about, but I'll punt for a moment, is what solves the problems that de Broglie was having and makes the pilot wave approach work, at least for systems of fixed numbers of finitely many non-relativistic particles, which is a very narrow kind of system.
Decoherence mean?
What's decoherence? Good. What's decoherence? Okay. So, when you want to calculate something in ordinary, familiar, classical probability theory, we consider all the possible ways it can be. We assign them probabilities. We add the probabilities together. It works out just nicely. Right? If you want to consider the average of something, what you would do is you would, consider all the different possible values a thing could have. You weight them by the probabilities, you add them together, and it works out just nicely. When you try to do the same thing with certain quantum systems, you get the wrong answer. For certain quantum systems, when you have superpositions in particular, right, you have wave functions that are superposed, what you find is that in general, in addition to the quantities assigned to the different probabilities, these extra terms, these extra factors, these extra things that come in and mess up the calculation, those things are called interference effects. They make the probabilities you calculate from quantum systems behave differently from what you'd expect classically, and they ruin the sort of pilot wave picture that de Broglie was trying to develop. But Bohm realized that if you take a system, a particle, and you actually have some kind of measuring device interacting with the particle, and you put the measuring device in there and you model it and describe it physically, like really put it in and try to treat it quantum mechanically, what you find is that interacting with this big, complicated measuring device with lots and lots of degrees of freedom, lots of moving parts, suppresses the interference effects dramatically. Suppresses them so much that now your probabilities look like they would look according to classical statistics. And that's called decoherence. It's the elimination. He actually first introduced it in chapter 22 of his 1951 book, and he called it the destruction of interference in the process of measurement. That's exactly what he called it, but now we would call it decoherence.
Now let's go back to the consciousness and our role in the universe.
I didn't finish. There's many worlds.
No.
We're talking about many worlds. Many worlds.
Just let me pause you for a second.
Yeah.
The observer doesn't need to be conscious.
No, not in
the
Bohmian
observer
mechanics.
could be any particle that interacts with it, and therefore consciousness is not needed for quantum mechanics.
It's not enough just to have a single particle, because to get decoherence to work, you actually need a lot of degrees of freedom. So, for example, one electron cannot measure another electron. Sorry. But a huge object made of lots of atoms can yield decoherence
So
on
when
a
did you
system.
become an observer? How many atoms do you need to become an observer?
How many hairs on your head do you have to lose before you're bald?
This is when I ask you a question. Can you please? No. Explain. Just tell us.
There is no definition of an observer in these pictures. There is no fundamental definition of an observer.
A decoherer.
Yes, please. Yes.
I've been thinking about some related questions, do some reading, and it's a fact that every measurement has an observer. Because if some conscious person doesn't look at the result, we don't know it was there.
The problem with measurement is an ill-defined concept.
Yes, that's right.
A decoherer, it doesn't need to be a measurer. It doesn't need to be an observer.
Exactly. The language of observers was required for the original axiomatic formulation of quantum mechanics, because the axioms say observers do measurements. What Bohm was trying to do, what people who were trying to provide these sort of physical interpretations of quantum theory, Bohm was an example, Hugh Everett with the many worlds interpretation was an example, is to eliminate the observer and measurements. And you just have systems. Some systems are small, some are big. The bigger systems cause more decoherence.
That's exactly right.
And more decoherence means that you're getting results that look more and more classical, but it's on a gradient. There's no sharp dividing line between what is an observer and what is not an observer.
But can you tell us how big is that gradient? In other words, above, I don't know, that much, it's a decoherer. Below it, it's not. And in the middle, we don't know. It's a fuzzy.
So because I work in foundations of physics and philosophy of science and high-energy theoretical physics, I didn't know the answer to that question, so I went and I talked to a friend, a chemist. Because chemists do worry about exactly those questions. They worry about when can you begin to pretend that things are more or less classical and not classical.
And it's okay if there's a big thing in between where we don't know. That's fine.
It's a blurry line, but it's around the size of large molecules.
Okay, like for example?
I think he said something like large sugar molecules, maybe, or polymers. I forget exactly what he said.
Okay, so like 10 atoms or something?
No, not 10 atoms. You need more like 1,000 atoms, something like that.
Whoa, okay.
100. Now I'm just. It's bigger than 10. It's smaller than a mole. I don't remember exactly what the number is.
Macroscopic phenomena like superfluidity and superconductivity that are macroscopic.
Well, okay, I should say at normal, okay, so at normal temperature conditions, right? Because you can have macroscopically many particles that still behave in a distinctly quantum mechanical way if you keep them very cold. So for example, squids, superconducting quantum interference devices, right? Or Josephson junctions. There are systems that under very, very carefully controlled, isolated, low temperature conditions, you can get distinctly quantum phenomena at large scales, but...
For a second, I have a question for everyone. Who's having a good time? Woo! Is this amazing? Who wants another 7 hours of this? Right? This is amazing. Thank you, Jacob. You're like, this is extraordinary. All right,
yes.
Let's open it up for a few questions. We're going to do a flash round. I'm not speaking anymore. Go ahead.
This is fascinating. I am not deep in my quantum.
And then at some point, you'll tell us about your own interpretation. But for now, let's open up for questions.
Yes.
So we'd like to go from history to the future. What are the big advances that are use cases that we can all experience in the next 10, 20 years that could cut like advances in my quantum?
Hypothetically, he has $1 billion to invest. What should you put it on?
Excellent. I'm glad you asked that question. Very glad you asked that question. If someone's got some money to throw around, where should they throw their money around? What would be a good thing to invest over the next 10, 20 years? Okay. So
they don't want to just throw it, they want to see it grow.
You want to see it grow. Okay, so I'm going to tell you right now. The number of spin-offs that have come out of like philosophy of physics, foundations of physics, quantum foundations, relative to the number of people who have worked in the field is staggering. So if I make a list of important things that have played a central role in modern quantum technologies, right? Quantum communication, quantum cryptography, quantum compute, like all of it.
GPS.
Atomic clocks, I guess. Yeah, that's right. Yeah. So if you want to make a list, right? And I mentioned decoherence, which came out of David Bohm's philosophical work on quantum theory, right? But there's entanglement itself. There's the famous EPR paper, which introduced the idea of EPR states, right? GHZ states and quantum Turing machines and quantum teleportation and important theorems like no cloning theorem, the no signaling theorem. So an extremely small number of people are responsible for these foundational results. And if our field of foundations of physics and philosophy of physics, quantum foundations, if our field got royalties, if every time a paper in atomic physics mentioned a GHZ state, we got a nickel, there'd be no funding problems in my field at all, okay? So the question, if you want to think about where to invest is, would another $1 million in quantum computing make a marginal difference?
No.
I would say no. And this is not to say that quantum computing is a bad idea. Quantum computing could be really great. But the cost-benefit, right, for quantum computing, you'd have to really spend a huge amount of money to make a major dent in that field.
Yeah.
So you want to look for fields that are significantly underfunded, like real funding opportunities, fields that are artificially, where the expectations are artificially low, but where you know that actually these fields are generating a huge amount of insights and a huge amount of things that end up playing a huge role in modern science. And I would humbly argue that philosophy of physics, foundations of physics, and the more philosophical side of quantum foundations are significantly underfunded relative to the contributions they routinely make through science.
Fantastic. Does that answer your question?
So if anyone wants to endow any professorships, this would be huge. This would have a huge impact on the field.
Let's restate the question.
I'm a boring use case engineer. I'm looking for what can I use advances in quantum from in the next 10 to 20 years. Give me some real things that I can hang on to.
Practical applications of quantum theory.
You can come back to it if you like.
Do we have anyone who knows anything about practical applications? Atomic clocks, sure, exactly, yeah. I'll give you one example. Okay, so I'll give you one example.
Every physicist in the room is allowed to answer that, by the way.
I have a ready-made example. I have an example right here, okay? So the project I'm working on, this is a new formulation of quantum theory, is not just an interpretation, but it also comes with it a precise mathematical relationship between the theory of stochastic processes, which is an old, non-quantum way to talk about systems that behave in a probabilistic way, and quantum mechanical systems. It's this mathematical bridge between the two things.
And its own meme coin.
And its own, what?
We could do a meme coin.
We could do a meme coin. Yeah, that would be great. Okay. Well, it's absolutely, but not quantum. Okay, look, it's quantum and not quantum at the same time. So, but here's the point, right? On the one hand, what this does is it provides a different way to think about quantum systems, because if every quantum system is mathematically dual or representable or equivalent to just a boring stochastic system evolving in some probabilistic way without all of the weird appurtenances of the Hilbert spaces and complex numbers and all of that, well, this perhaps sheds some light on what's really going on under the hood of quantum theory. And that's interesting from a metaphysical point of view. But now we can turn it around and say, well, what if I've got some really complicated stochastic process I'm trying to model? A process that's like complicated. Maybe it's a process that goes beyond the usual approximations we like to make. There's this famous approximation called the Markovian approximation, which just says that we can ignore like past effects, right? We make this approximation all the time, but what if we can't? What if we have a system that's distinctly non-Markovian? Well, it's not clear how to simulate those in an efficient way. But with a bridge between these kinds of systems, these non-Markovian systems and quantum systems, there's the possibility that some of these systems that might have been very difficult to simulate on a computer, that might have real-world applications, may be efficiently simulatable on quantum hardware. All you have to do is take the process, which is some non-Markovian, very complicated process, figure out what kind of quantum system it corresponds to, and then see if you can build that kind of quantum system on quantum hardware in a quantum computer. And so there's the hope that you might be able to simulate some very difficult stochastic processes that could have practical applications throughout the sciences and economics and finance and current whatever, right? That some of them may be efficiently simulable on quantum hardware. Unfortunately, we don't have any quantum computers around. But one day if we do, this potentially could be a new use for quantum computers. One of the big mysteries, say what?
How big do you need them to be?
I don't yet know. But I'll just say, one of the big mysteries about quantum computers
qubits?
Don't know yet.
Okay.
But one of the mysteries about quantum computers is, what are they good for? You might think, well, quantum computers, right? They take every classical computation, they do them all simultaneously, right? And that's why they're powerful. But it turns out that's not how they work. They don't work that way. So many things you might think they'd give you a speed up for, they don't give you a speed up for. There's actually a pretty narrow set of problems that quantum computers, at least as far as we know, give you an appreciable speed up with. Famously, one of them is cracking RSA encryption. So a quantum computer would make it very efficient to crack RSA encryption, prime factorizations, that kind of a thing. There are a couple of other problems that we know that quantum computers could be very useful for. One of them is just simulating quantum systems very efficiently. This could open up a whole other avenue, right? Simulating very complicated real-world non-quantum stochastic systems using quantum hardware. And anytime you find some potential new use for quantum computers, that's a potential thing that they might be useful for.
Can I ask a question there? When you said Markov systems, I'm wondering about the thought that there are concepts, mainly in finance, that past information tells you nothing about where the next move will be in something. Is that maybe too limited a view? If you had enough quantum computing, could the Markov process be different? Is there information in the past?
Well, you said there is.
Yeah. So now, to be clear, I am not an expert in finance or in algorithmic trading or anything that's super related to this. So you couch anything I'm about to say here with a huge grain of salt.
By now you've convinced us anything you say will take...
there is a very narrow set of subjects of which I have any sense whatsoever. Anyone who knows me would know that. But okay. But I'll just say, one always runs the risk when modeling anything that one is making too strong an approximation in some way, right? But of course, we have to make approximations all the time. I mean, there's an old saying that every model is wrong.
Yeah, because it's an abstraction.
Absolutely. Every model is an abstraction. Every model entails some kind of simplification so that because if we try to do the whole thing all out, it would just be the original thing, right? A model is by definition some kind of simplification that we can work with. And we always have to make some kinds of approximations. The question is, are all those approximations legitimate? Are they all justified? Now, if there are good, strong grounds for justifying the Markov approximation, the idea that all we care about is the present when predicting the future, if that's justified, well, then make it. But if the only justification is, well, that's where the light is, the lamppost is shining there, so I'm going to look there, I just don't know how to do anything else, that's not a good justification. And I would say that having a formalism for being able to handle in an elegant, potentially efficient way processes that do take the past into account would be useful. Useful at least to model and see if it's useful for finance.
On to the flash round. Raise your hands. Go ahead.
So
introduce yourself.
I'm Samson. I'm a pediatric nephrologist and also run a computational genomics lab. And this has been fascinating. I'm taking with a little bit of it. The modeling that you're talking about and measurements, in health and disease, we make measurements all the time. And historically, we've come to understand human health and disease through classical physics. The heart is a pump. There's diffusion. There's chemistry. Does any of the things that you're talking about, space and time, waves, is that going to help us understand how molecules work in cells, or how cells work together, or how a doctor measuring of blood pressure impacts the way we interpret it and what we do about it?
My answer to that question is most likely no, at least not directly. However, there could be indirect consequences for how you do medicine. And the reason is because one way we do medicine is using causal modeling. And this brings us, now, you see how cleverly segued back to the sort of question about what causation is, right? So, if you're thinking about the heart as a pump, I mean, the heart, whatever model of quantum theory you have is probably going to, we're going to demand of it that it's able to replicate the observed behavior of macroscopic classical systems. The heart appears to be a big macroscopic classical system. Some of us have bigger hearts than others, but all of our hearts appear to be big enough that we can treat them classically. But if you're trying to do drug discovery, right, if you're trying to understand how certain medical interventions will have a causal influence on the outcomes of diseases, you're interested in a subject called causal modeling. And causal modeling has become a very sophisticated area of statistics, a very sophisticated area of double blind, random controlled, randomized, double blind studies, these sorts of things, right? We're doing causal modeling. We have a set of variables, a set of things we're trying to study, and we're trying to understand how they're related to each other. Right? We're trying to understand how, certain quantitative features of some physical condition are related to other conditions, or related to medical interventions or drugs, or
it's two ways. You want to have a causal modeling to understand why it's happening, predictive modeling to say what will that intervention end up impacting in the future.
That's correct.
So how much increased explanation or causal explanation will come from incorporating some of those theories you want?
So not directly. But the causal modeling framework gives a very interesting way to think about causation itself. Okay, so for example, if you want to understand why we think a certain drug has a certain effect on a population, right? Of course, we will administer the drug to some of the population. We'll not administer it to the population. We're basically controlling a variable, and we're studying whether there, the correlations, the statistical correlations that show up. And we're not just looking for correlation. We're looking for causal relationships, right? Correlations imply causation. And in order to suss out causal relationships, not just statistical correlations between things, we have to have in mind that we can do interventions. We have to imagine that some agent, the agent being the person running the study, can choose to activate a variable or not activate a variable, and then suss out, what kinds of consequences we get from this. This is the do operator.
But in an observation-independent way. That's the whole point of double blind.
It is in an observation-independent way, but it does rely on the idea of an agent doing an intervention. Okay. And this idea that we do causal modeling with this interventionist conception of causation has become pervasive and how people talk about causal modeling for good reason. Because in everyday life, when you're doing medical testing or you're trying to understand interventions of a more general kind, it's not medicine, right? We do have people, and people are agents, and agents can choose to intervene or not intervene in certain ways, and we can study the correlations that result from them. That's how we can suss out causal relationships.
As an agent, can I intervene? So I want to open this question to the whole room and rephrase it a little bit. How much evidence is there that biology is dealing with quantum effects, and in what biological processes have quantum effects been observed? There are some theories that consciousness arises from quantum. Let's turn it off, please.
Physiology governed by some quantum.
That's exactly right. And this is a question for everyone here. For example, microtubules in neurons have been postulated to have quantum properties. I have absolutely no qualms with so many different aspects of biology very early on. It doesn't need to be humans and the epitome of evolution as we like to think, which is ridiculous. Anyway, but it could be bacteria, it could be like bats, it could be anything that's doing some type of sensing or some kind of, reaction. My guess is within one of the most ancient processes of the OXPHOS, oxidative phosphorylation in sort of mitochondria energy production. I'm sure there's quantum effects being exploited, but I'm not an expert, so I'd love to sort of open it up.
Who's going to give a very brutal answer to this response?
Brutal answer is the only thing we take.
Yeah. So I understand this. I would say that this is a reversible proportional to how much we know about the system. Because I think that we are using this possibility in biology to replace the lack of measurement effects or the lack of detailed, signal. Yeah. Because you mentioned incidentally
the two things, or maybe the three things that we know the least about it, which neuronal function. And you measure a little bit of microtubules and the early life.
I see where you're coming from.
I'm not saying that there is not quantum possibility there, and I don't know how it manifests itself. But the only thing I'm saying is that we shouldn't be forcing it in areas that are less explored.
Yeah. So I work on a lot of fields where people will use that field to explain stuff that they don't understand. For example, epigenomics. They say, oh, it must be an epigenetic effect. I'm like, bullshit. So I did not say these just because we don't know much about them. On the contrary, I say them for very, very specific reasons. But we have a neuroscientist up there, in psychiatry as well. I'm curious if anybody wants to take this on with, yes, there is quantum here, because that's what I think you're getting at, right? So John, go ahead.
Household photosynthesis.
Yeah, exactly. Yeah, so that's at the limit of physics. And let me make a very quick trivia here. It's a parenthesis, but I think you guys are going to love it.
Just make sure to close the parentheses, otherwise you'll get an error.
So in a sequoia tree, where does all the biomass come from? Very simple interpretation is, it must be the soil. It just sucks up nutrients.
It's the carbon.
It's the carbon. The decarbonization of the atmosphere, all of the wood actually comes from exactly that process that John just mentioned. So the fixing of carbon atoms.
And when you lose weight, where does the weight go?
Why is that quantum?
Go ahead, John. Why is it quantum?
Photosynthesis is a quantum effect. Well, why is that talking about that?
It has very defined chemical reactions that they can be reproduced, order, and interfere in a measurable way. So if I understand anything from the lectures about quantum...
So quantum does not mean uncertainty.
It's here. Probably when the photon hits something, then there's a quantum effect, and then the reactions.
Well, then everything's quantum, which is fine, because it's not explanatory.
Yeah, go ahead. We
has been established.
Olfaction.
There's a well-known phenomenon in olfaction that is best explained and predicted. It's measurements are accounted for by a quantum representation. So that's where, unlike consciousness, where you can't measure anything.
Well, let me just.
But this is the flash round, so I'm happy to go to the next question.
Oh, okay. I want to just ask what you meant by consciousness coming out of quantum mechanics, because
we'll come back to that.
Okay.
That might be the ender.
Sure.
Okay. Flash round. Continue. Go ahead. If he has to look at his phone, that's a problem.
The naive questions are always the best questions.
What was that? What type of question?
A naive question.
It's a naive question, an advanced naive question.
I love it. You're not trying to impress.
Does quantum field theory naturally explain non-locality, since there is only one electron field everywhere?
Does quantum field theory naturally explain non-locality? So the problem with the word non-locality is it needs to be precisified.
So, okay.
What do you mean by non-locality?
No, but this isn't me being. No, this is not me being an annoying philosopher. There are different definitions of non-locality. I need something more precise before I can answer.
Give us a few options.
We have two electrons that are entangled.
Yes.
They were here one day, and then they were brought apart. One is on the moon, one is on the Earth.
But no one has observed.
You make a measurement, whatever that is, on one, and you determine the spin of the other.
There appears to be something weirdly non-local going on. Does quantum field theory resolve that problem? It does not. No. Quantum theory does not resolve that problem. Quantum theory does not answer any of those fundamental problems about quantum mechanics.
But since you have only a single electron field everywhere, okay, I guess.
The electron field is delocalized, distributed throughout space. Yes.
You can entangle a photon and an electron too, and then you have two different fields, right? So,
quantum field theory does not resolve the fundamental problems of quantum mechanics, the measurement problem or the problem of non-locality. Yeah.
A very naive question. That assumes that nobody has observed either of the two during that entire time that they've been apart, right?
But notice something really important about this question. Notice that in all these discussions about non-locality in quantum mechanics, going back to Einstein, Podolsky, Rosen, the EPR paper, and the example you just, there's a particle here, there's a particle, they were interacted, they entangled, they went far away, and then someone measured one of them, and someone measured the other one. Notice you've got agent interventions again. You've got observers playing a central role in this picture.
Oh, they hit something, right? If they hit something.
Yes, the observer. If they hit something and it doesn't count as observer, and you don't do like don't do the axiom.
If one of those particles are entangled, hit the moon, and the other one is just drifting in empty space, right, to the other direction.
Yes.
If that one, had its spin determined at that moment, it determined the spin of Young.
You said it had its spin determined. What do you mean by spin determined?
Meaning that it now has, in that moment in time, it has, were I to, okay, were I to measure it,
were you to measure it, yes.
So, I mean, okay, then you can say, okay, nothing is real, we're not here.
But no, but you see, that's exactly the point, right? If you get rid of the idea that there's a fundamental axiomatic role to be played by the observer, eliminate the observer and just go back to the, so look, before the advent of quantum mechanics, physics had moved into a very impersonal picture, right? The Laplacian paradigm of physics is there's just a bunch of stuff everywhere, particles moving around, different positions, different velocities, and a giant differential equation describing how this state of the universe was to be updated moment to moment. There's no role for observers. There isn't even a role for causal influences between things. Observers, causal influences, these are all just colorful language, descriptive language, ways to summarize the things you're seeing, ways to paint a picture, but ultimately all of it is irrelevant, right? And then quantum theory comes along, and suddenly the observer comes right back in again. The observer plays this central role. A lot of the interpretive approaches to quantum theory, not just mine, but Bohmian mechanics, all these other approaches, demote the observer back down to being an ordinary system. There's no fundamental role to be played by the observer. When you have entangled systems, and some system comes along, like the moon, not an observer or whatever, and in some way interacts with the particle, there's no collapse that happens. And so the seeming causal influence that's supposed to be traveling like superluminally, it actually becomes much more murky to say that's happening in this picture.
So Jacob, can I jump in for a second? So let's talk about the moon for a second. So basically you have this entanglement and there hasn't been a human observer, let's say, but this touches the moon and now you've just kicked the can down the road. You've basically passed the uncertainty to, the next, like every time it bounces somewhere, that secret gets propagated and carried along. And sort of my trouble with all that is the concept that there hasn't been an intervention to either of these two particles is something where it fundamentally breaks down. This whole sort of non-locality assumes that, hey, nobody touched that for a while. And then there needs to be, of course, some communication and coordination for nobody to touch it, so that eventually I can kind of like pass that information over there. And then, yes, that thing gets observed, and I know something about here, but to even pass that information back is, just...
When Schrödinger introduced the term entanglement, so Schrödinger wrote in German, he also wrote in English. He introduced the word entanglement. He introduced this word in 1935. And the paper in which he introduced the idea, he talked exactly about what you're talking about. He called it a regress problem, right? That as systems...
tracing it back.
Systems, interact with entangled systems. More and more systems start to participate in entanglement.
And he called entanglement the secret.
He said entanglement was not one, but the feature that in his mind made quantum theory different from pre-quantum physics. He was very clear about this in the opening page to this paper. So this infinite regress question is a very interesting question, but here's the thing. When you take a physical theory, an unintuitive physical theory, and we've had lots of unintuitive physical theories. Special relativity is a great example of an unintuitive theory. Okay? Unintuitive theories often lead to situations that prima facie look paradoxical. Right? In special relativity, there's this famous paradox, not really a paradox, called the twin paradox. The twin paradox is the statement that if I am moving relative to you, then you will see my clock running slow, but I will see your clock running slow. How can I see your clock running slow and you see my clock running slow? That seems to be a paradox, right? It seems obvious that there's some kind of paradox that I see your clock running slow, but you, because I'm moving relative to you, you see my clock running slow. This can't both be right. But when you carefully try to pin down whether this paradox is really happening, if you very, very carefully describe the situation, describe how you would actually check to see if the paradox is happening, you find it doesn't happen. You find the paradox doesn't actually happen. The paradox was an illusion. The non-locality in quantum mechanics, at least if the non-locality is to be given a causal valence, you're to think this non-locality is not just the kind of non-locality where two things are correlated, but that there's some kind of influence actually propagating faster than light. It does seem kind of like there is. And when you model quantum systems in the traditional way with observers doing interventions, it looks like causal things are happening because, and this goes back to the causal modeling. When you think of causation, causal modeling in terms of interveners, agents intervening, and that's how you define causal relationships, it certainly does look like there's a causal influence propagating. But if you remove the observer as a fundamental primitive from the axioms of the theory, if you do say, no, don't talk in terms of Alice and Bob as observers, tell it to me in terms of the atoms. What are the atoms doing? Tell me the story of this causal influence propagating at the level of the atoms.
Then just
the
breaks down.
microphysical
There's
level.
none of that, basically.
It goes away because there's no interveners, there's no agents anymore. And so what you need now is to find some other way to talk about causation. You need to do some other definition of causation. And there was one person who did that, John Bell. In John Bell's second version of his famous Bell theorem, 1975 paper, The Theory of Local Beables is what it was called, it's the term Beables, he tried to find a version, a way to formulate this non-locality in quantum theory that showed that it was causally non-local, that there was causal influences propagating instantaneously, but without relying on agents and interveners. He tried very hard to do it, and arguably he did not succeed. So it does look on the surface like some non-local causal factor is happening, but if you try to phrase it in terms of the atoms without a good, robust theory of causal influence, it's very hard to say that's happening. Bell tried to do it, but arguably he was unsuccessful.
Okay, last chance for questions. People who have not spoken before.
A lot of us probably heard this stuff when we were, 22-year-olds or 20-year-olds, inspired by learning just a scratch more than high school physics. And I'm struck looking back, 30 years hence, 35 years hence, how you're still, just then you're quoting a 1975 book, right? Can you give us a flavor of what's happened in the last 50 years? And I wonder if you're just not saying much because we're not smart enough.
We're not ready. We're not worthy.
To get it. I mean, that would be a theory. But if you could, are we really that frozen that we're still talking about these 150-year-old theories as if they're the stick of the art?
Yes.
That's all I needed to know.
Well, Jacob, you wrote your paper. You're up with it.
Yeah, you're on.
I'm gonna slightly expand on that just a little bit and just say this. This thing that we're doing here, this thing that
the decoherence.
No, this thing that you have brought into being, this intellectual exchange, this discourse that we're engaging in right now, this intellectual engagement that we're experiencing right now, there is so little of this in physics right now. You might think, well, I'm in a physics department. We must all sit around in a physics department and talk like this and talk about what's going on. We do not.
It's not because we're all amateurs.
This is like right?
No, this does not happen in physics departments. That does happen in philosophy departments. It does not happen in physics departments. Okay? Why does it happen in physics departments? Complicated historical reasons. Now, in the first half of the 20th century, right? You look at the great physicists in the early 20th century.
That was happening.
Right, that was happening all the time.
Yeah.
Right, they were deeply engaged with philosophers. They were deeply engaged with the Vienna Circle and the positivists, and they were reading Karl Popper, and they were arguing about Schopenhauer, and they were all claiming on all sides of the debates about quantum theory that they were the true vicars of Kant and Kantian philosophy. All of them were doing that, right? And then something shifted in the intellectual environment in physics. And the best I can say is it was the war. It was the shift of physics to America, and it was also money, okay? When there's a lot of money at stake, people suddenly feel like they're in a huge hurry to get concrete practical results. There's no time to sit around and talk about philosophy.
It would be good then for you to study finance.
All right,
Or make
more questions.
We need more of this. I'm saying we need more of this.
Right here and there, right there. Those two.
Can you give us some sense of what is beable? I mean, it seems like what is reality, right? You told him waves are not it, maybe the fields are. I can kind of have a sense what observable means, but what is what at least in the
You, sir, are a Beable.
He's a bee. No, he's actually instantiated.
You are a no. So not just be able. Your be is no. So what I mean by this. So I don't know what the fundamental beables of nature are. We don't yet know the fundamental beables of nature. Now, if you
gut feeling of what
well, I mean, we don't know. I mean, we're aware of atoms. We think atoms are made of smaller things, maybe electrons. We don't know what the most fundamental constituents of nature are. Electrons, photons appear to be manifestations of perhaps quantum fields. Maybe quantum fields aren't fundamental. We don't know what the fundamental beables are. However, just because something is not fundamental doesn't mean it doesn't exist. Imagine you came in from a rainstorm and you're covered, you come in and you say, gosh, I'm really wet. And your friend says, no, you're not. You go, of course I'm wet, I'm clearly wet. The person says, no, you're not. You're like, well, in what sense do you say I'm not wet, sir? And your friend says, well, at the level of the individual water molecules, wetness doesn't exist. Water molecules are what are fundamental. Wetness is not a fundamental thing, therefore it doesn't exist. And you go, oh, come on. Things can exist without being fundamental. You exist, even though you're not fundamental.
Jacob, I have an answer to your earlier question. You asked me what's a miracle. I have an answer. Do you want to hear it?
Yes, please.
Okay.
What's a miracle?
I was talking earlier about wishing for something, and then that wish needing something non-causal and outside the cone of the present and the future to happen. And I have the distinction between a miracle and the opposite. If I want something done, I don't just wish for it, I make a phone call and I cause the series of causal events for my reality to come through, and I just expect that it will appear somewhere in that cone of future possibilities. A miracle is a wish that does not causally result from that cone outside. In other words, a miracle is something that I should have done earlier if I wanted that to happen. And I'm sorry for saying this so openly, but I think it's hopefully a lesson to all of the young people in the room. If you want something done,
You should have already done it.
Should have already done it. Exactly.
start working on that cone ahead. Don't worry about that non-causality. Anyway, so, but on the beableness,
I don't know what the fundamental beables are, but I do know that at some emergent level, there are non-fundamental beables like yourself.
So Jacob, tell us now about your view. We talked about the Copenhagen view, about a few other views. Tell us about your view.
Good. So my view is that physical systems have actual physical configurations, just like we would have imagined in the pre-quantum world, but that the laws we didn't have, that we couldn't come up with back in the early 1920s, they couldn't come up with the right laws in the 1920s because they were stuck in some old paradigms. They thought laws had to be Markovian. All the known physics up until that point was Markovian. You know what's going on right now, you can predict the future. They were working on this in the 20s. This was before there was a modern theory of stochastic processes. This is certainly before people were talking about non-Markovian stochastic processes. Yeah, there was Brownian motion, there were Wiener processes, but like a sophisticated, comprehensive theory of stochastic processes, certainly outside the Markov approximation, was unavailable. And as best I can tell from having plumbed this literature in depth, there is nobody who conjectured that you could take classical-like ingredients, physical ontology, physical configurations, and give them non-Markovian laws and see if you can get quantum mechanics out of it. This was never done by anybody.
So
ever.
What you're saying is that just non-Markovianism.
Non-Markovianness alone is not enough. You need a particularly strong form of non-Markovianity called indivisibility. It's called indivisible stochastic processes. The term was introduced in a 2021 review article.
Explain what's indivisible.
Explain what's indivisible. Indivisible is that which cannot be. Okay, sir. No. So what makes a process indivisible? So standard Markov process is one where you specify what is going on right now, the present, and then you have a law that tells you what happens later. Okay. If you know what a Markov chain is or a Markov process, these are processes where you can kind of concatenate these. You can do the evolution of the system in steps. You have, at every moment, you've got a law that tells you what happens next.
That's the divisibility, basically.
You have another one that happens next to it.
And it's
notice you can
temporal.
divide it up. Exactly.
Yeah, got it.
Yeah. And an indivisible process simply
ticking
fails
clock,
to have that
basically.
property.
Got it.
It fails to have the property that you can take any duration and break it up into subdurations that have lawful descriptions.
Got it.
Exactly.
Beautiful. Thank you.
And once you get that up, you have a much more general class of processes that naturally exhibit phenomena that look like interference. And if you want to know like why quantum computers are so useful, there's another interpretation of quantum computing, Manolis' interpretation, and one of the reasons why David Deutsch, one of the founders of quantum computing, wanted to develop quantum computers was to prove that Manolis was right, because he said quantum computers can do more than classical computers can do, and the only way to explain this is that they're doing the calculations in all these parallel universes. But he was very disappointed. We were all very disappointed when we discovered that many calculations cannot be made faster in quantum computers. And then people began to wonder, well, if there really are all these many worlds out there, and the calculation really is happening in all these worlds, why is it that so many calculations cannot be made more efficiently on quantum computers? This strongly suggests to me that those other worlds aren't really there, and that you're getting the advantage for quantum computers from a different source. And the different source is if you try to model a computer using Markov processes, and all computers basically are Markov chains.
Sure, 'cause
They're
there's a clock.
deterministic Markov chains,
Yeah.
Markov chains. Once you allow yourself to have not just probabilistic computing, but indivisible probabilistic computing, you have a much more general set of systems. And with more general sets of systems, you can do more things.
Good,
and
but they're less predictable because of basically the
they're less
clock
predictable.
allows you to sort of know.
And which things you can do that give you an advantage over the classical case is not obvious a priori.
Amazing, thank you. All right, next question.
Chris Flynn from Fidelity Investments. Thanks a lot. This is fun. You kind of answered my first question, but is there a way to actually observe or measure a quantum system without actually physically interfering with it?
Alas, no. However, there is a very interesting protocol known as weak measurements. It was introduced by some quantum foundations people, interestingly enough. Aronov is one of them. So Aronov was involved, a couple of the people involved. David Albert was involved. He went from physics to actual philosophy. So a lot of people who work in philosophy of physics started as physicists, which he did, and ended up doing philosophy of physics. Weak measurements work in the following way. Don't study just one system. Take 10,000 identically prepared copies of your system, and don't do we call a projective measurement. Do a very, very, very gentle measurement. Interact with it in just the most gentle way. Now, if you do this in this very gentle way, you're not going to get an answer from each system. The interaction is going to be so weak that when you so you send a measuring device in, you let it interact super duper weakly. You then bring the measurement device out and you look at the measuring device. And you gain very little information about the system you've measured. Very little. But the benefit, though, is that you don't lead to this projective collapse happening to the system. And you might go, well, but if I'm not getting any information out of it, what's the point?
It's a partial collapse.
Decoherence of it.
That's right. You very, very gently. But you do this with 10,000 systems, with 10,000 of them, and they're all identically prepared. And for each one, you just very, very slightly graze it. Just get a little, just scoop a little bit off the top, just a teeny little bit off the top, right? And you collect all the data. You can actually gain some information from all the data. Now, here's where the interpretational problem comes in. So this is an experimental protocol that you can actually do. You can do this experimental protocol. You can actually do this, and lo and behold, you'll get results on your you'll take all the data, you'll put them in a computer, and you'll get a number out. And the fact that you can get a number out from measurements made everyone super excited. There's a kind of philosophy, not small p philosophy, a kind of attitude, right, towards science, that if you can do a measurement on it, it's science, and that makes it great, regardless of whether you have any good interpretation for what you're doing. There's no question we can do these measurements, these so-called weak measurement protocols. People have been doing them. The question is, when that number comes out, what the fuck does it mean? Right? And there's been a huge dispute over the years. Like, you get a number, okay, but what is that number telling me? It's not, I haven't done a standard measurement of my quantum system, so I can't say I'm measuring some property of my quantum system. I get some number. What does that number mean? And people have tried to interpret what that number means, and they've said some rather outlandish things about what that number is. And the question about what that number means is now kind of a almost philosophical question. So yes, there are ways to do measurements where you're barely interacting with the system, and you can get a number out. And I should say the number does have a mathematical significance. The number is computing what's called a matrix element of a self-adjoint operator. So there's but the question is, like, what is it? Is it telling you something physical about the system that you are measuring? And that's very murky. So what I would say is that, at least according to the standard picture of quantum mechanics and all the interpretive frameworks that we know of, to get an actual, reliable, robust result out of the measurement process, you're going to have to get a decoherent process involved, and that will inevitably produce some deviation or change in the system. And one way to see this is just that measurements in quantum mechanics are inherently non-commutative. If you measure A, non-commutative. If you measure property A and you measure another property or observable B, and B has to have a certain feature. It's got to be incompatible with A. It has to satisfy what's called a complementarity relationship or uncertainty principle. But if you measure A, then B, then A again, you may get a different answer for A. And no matter how gently you measure B, as long as you measure it strongly enough to get some reliable, robust information out, then invariably there will be some consequence for the measurement of A.
Final quick question.
Yes.
It's a very small one.
Yes.
What's the relationship between consciousness and quantum?
Okay. Small question.
We save the easiest.
Save the easiest for last. There is absolutely no way that I can answer that question without telling a little story. Can I tell a little story?
We'll take the story.
Okay. How many of you have ever heard of Mary's Room? A couple of people have heard of Mary's Room. So philosopher Frank Jackson introduced a thought experiment called Mary's Room. Mary's Room works like this. Mary is a super brilliant scientist. She lives in a sealed room. And in this sealed room, everything is black, white, and shades of gray. Even her skin. Somehow they've just, altered her skin. She has never seen a color before. Never, ever, ever seen a color before. But she's very smart. She has access to a black and white grayscale version of the internet. She has access to all the information there is. She has advanced scientific equipment. She's got an electron microscope. She can even call in people. Of course, they have to be decolored before they come in. And she can slice their brains open, and she can peer in their brain. She can electrode. She can do absolutely everything, and she has unlimited intellectual ability. Can she ever cross what's called the explanatory gap? Okay, so I have to see what the explanatory gap is. There are two problems in the philosophy of consciousness, the easy problem and the hard problem. The easy problem is not an easy problem. The easy problem is, will science ever get to the point at which we can have a sufficiently sophisticated model of the brain that we can describe and explain the behavior of conscious beings? And most people would say that's a hard problem, but you could imagine science getting to the stage at which maybe with enough technology and we can model brains and simulate them on sufficiently powerful computers, we can say, okay, when a brain is conscious, it does these things, we can predict what it will do, at least probabilistically, and others it can't. So that's still a pipe dream at this point, but maybe one day we can imagine doing it. The hard problem of consciousness, this was coined by David Chalmers, a philosopher, is, okay, well, once you have that model, why does it feel like anything? What about the subjective experience? Like the fact that, the brain does these things. There are these sort of neural correlates, these states of the brain, neural correlates of conscious experience, the neural correlates of consciousness, NCCs. But like, why do they come along with redness, like the distinct feeling of redness? And now there are people who doubt that there is a hard problem. They're like, oh, it's an illusion or something like that. When Mary's Room thought experiment, part of what it's supposed to do is, now technically what Mary's Room was originally introduced was to argue against physicalism, but I read it in a different way. Mary can do all science. All the science you could imagine. She's immortal. She can do science for centuries. She can develop all the science you could imagine. She can do every experiment ever done. But will she ever, and she may even be able to get to the state at which she can like figure out what to do to her brain, like which electrodes to push so that she'll have an experience of red. Okay, maybe she can even do that. But can she ever explain how you get from the physical thing in the brain to suddenly having the experience of like the actual color? Like how do you get from like the physical stuff? Where does that come from? That's the explanatory gap between the easy problem and the hard problem. And there are many people who doubt the hard problem is solvable precisely because of the Mary's Room argument. Because even if you imagine unbounded scientific expertise, even if you could characterize, okay, this brain state corresponds to feeling red, this brain state corresponds to feeling green to blue, you have the brain states written down, but you still don't know why they come along with these particular feelings. And that's the hard problem of consciousness. Now, some people doubt it exists. I feel sorry for you if you do. But so now let's go back to the quantum case, okay? Suppose we were able to say, okay, certain brain processes inherently use quantum mechanical phenomena. So what? Does that get us across the gap from the easy problem to the hard problem? Just because quantum mechanics is happening in the brain maybe and playing an instrumental role in certain processes, even if you know that, even if you can model that, okay, well, how do you get from that to, and then when this is happening, this is how I'm going to, redness, this is red. I'll actually have experience of red. And when you first have that experience of red, when Mary first has experience of red, she's learned something. When she leaves the room for the first time and suddenly sees color, something new has been learned to her and she doesn't know why. And none of her scientific experience up at that point can explain why suddenly she's having these experiences. So I think the hard problem is not solvable, and I think that's just fine. I think there are deep problems in nature that maybe we'll never be able to get to, and I don't think that understanding whether quantum mechanics is working in the brain or not is going to let us transcend the explanatory gap from the easy problem to the hard problem. That's just my point of view, and I could be wrong.
Sorry, you think it's insolvable in principle or just not solvable with our current model?
In my view, it is insolvable in principle. The hard problem, insolvable in principle. That's my view.
Mary's Room is not a kind of argument for the possibility of AGI.
Well, that's an interesting question, right? So is Mary's Room an argument against AGI? I don't necessarily think so. AGI might be just the easy problem. That is, if we can figure out how to model a system that behaves consciously, could we simulate it, and wouldn't the simulation be AGI? Artificial general intelligence, like a computer that really does behave like indistinguishable from human. However, if you then ask, does that computer have internal subjective experience? That we can't know. And I don't think any scientific investigation will tell us the answer to that. There's a term that was introduced before David Chalmers in the 70s called the P-zombie, which haunts the nightmares of metaphysicians all over the place. The P-zombie is not, zombie. P-zombies function and observably behave exactly like conscious beings. They're like your AGI computer, carefully designed so that it simulates the same exact processes that go on in the brain of a normal human being. And it's plugged into a robot, and the robot looks like a person and walks around and talks and says, oh, that hurts, oh, that feels bad, or I see red, or whatever they're saying, right? Okay. But does that computer have it? Is there something that it is like to be that computer? Does it have an internal subjective experience like the kind that we believe we have? If it does not, it is called a p-zombie. Now, there is a view among some metaphysicians and some philosophers of mind that p-zombies, philosophical zombies, it's short for p-zombies, are conceptually impossible. They're inconceivable. That anything that behaves sufficient like a conscious being, outwardly, that satisfies the requirements of, okay, we solve the easy problem for it, it behaves like a conscious being, then it is conscious. It has the full consciousness, it has internal experience, and it's not sensible to even be able to talk about it lacking that internal conscious experience.
As somebody who studies neuroscience and biology and all of that, and by the way, our next salon will be on consciousness. What if we're just faking it? In other words, if you look at the neuronal basis of subjective experiences, there are many experiments where, for example, if you cut the corpus callosum, you can actually have part of the brain unaware of the commands that were given to the other half that then led to an action.
Yes.
And that part of the brain that never saw that command will interpret the action as something that it really wanted. And then the question is the brain a very, very good employee who just never wants to be caught not knowing and who will always make up a story, including when asked, why are you thinking? In other words, do we know that we ourselves have any consciousness beyond what we are, claiming that we do? And yes, sure, your answer was very provocative by basically saying maybe you don't, but I do. There's no experiment that can prove to me that any of you have a consciousness.
Correct, yeah.
However, if I disconnect myself from my brain, maybe my brain is saying, oh yeah, of course, you're super conscious. Here's all the great things that you have that prove to you that you're conscious. Why would I believe it?
Consider a world in which all the humans are p-zombies and lack internal conscious experience, and a world in which they in fact have internal conscious experience, and they'll observably look the same by construction. And this just is telling us that we're probably not going to be able to get at this question.
But if you transport yourself from the self to the other person looking at the self, is there anything you can do to prove that you're actually conscious?
Like I said, anything you could do in a world without internal conscious experiences, but p-zombies, could be done in a world with internal conscious experiences. And so I don't think that any external invention
is there something in the opposite direction?
Before we go on, I do want to tell a joke. Want to hear a joke?
Of course.
Here's a joke. I told this joke to David Chalmers, and he liked it a lot. Okay. So here's a joke. And those of you who have some background in high energy theory will enjoy this joke, okay? Okay. What do string theory p-zombies eat?
Brain?
P-brains. He sent me, you know what he sent me in a response? I sent him that, and he sent me back a zombie emoji. I have a zombie emoji from David Chalmers on my phone. I've saved it all these years.
All right,
guys.
So I remember the part where we were going to end by 7:45. I looked at my clock and I'm like, oh, is it maybe 7:55? It's 8:55. Who had an amazing time tonight? So, Curt, Jacob, I can't thank you guys enough. Thank you for gracing us with your extraordinary thoughts, and also with bringing so many new guests to our salons. Somebody commented, ooh, the crowd looks a little different. There's more energy and all of that. So this is you guys. So thank you to all of the first-time comers. I hope you will continue coming. Thank you to all the old comers who are repeat comers. And again, thank you both so much. It's been extraordinary.
Thank you for the invitation. I mean, it's lovely. And thanks, Curt, for
contributing.
It's
been amazing.
New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, hey Curt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts? While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Curt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook, or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for theories of everything, where people explicate toes, they disagree respectfully about theories, and build as a community our own toe. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in theories of everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, toe listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/Curt Jaimungal and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on Toe full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.